We're talking about the area between curves. Now, we've actually already done that. When we first started off, we drew this sort of picture. Yeah. And I said, let's compute the area underneath this curve between A and B, and what's the last bit? Above the x-axis. Right? Now, I can actually view the x-axis as a curve. Okay? Now, remember, when I use the word curve, I actually mean the graph of some function. Right? What's the function that gives me the x-axis? Y equals 0. Right? So here I have some function y equals f of x, and here I have a function y equals 0. So we actually already did this, in a sense. But we want to generalize it. Right? We want to be able to, instead of having y equals 0 be our bottom curve, perhaps have another curve, y equals g of x. Right? We'd like that to be our bottom curve. And then compute just this area. Okay, so how should we do that? Okay, why is this going to work? Okay, so here's what Jenna's idea is. You start with the area under f of x, above the x-axis, and then we subtract the area which is coming under g of x and above the x-axis. Okay, so Jenna's idea is to say, okay, look at this integral, which gives you this whole area, and to subtract the second integral, which just gives you this bottom area. And when you subtract, then you'll be left with this top piece. And of course, what can I do with these two integrals? Make them one integral. This is just f of x minus g of x. So intuitively clear. Now, this seems to be working fine in this nice case where both f of x and g of x are positive functions, right? Or non-negative functions. But what's going to happen if g of x, say, is negative? Is it still going to work out right? So if you add it, which means, what do you mean we have to add it? Calculate the area underneath, Now, so here again, we're getting into a problem because of the way we talk about these things. All right? I keep using the word area. But as soon as we get down here, right, is it computing area anymore? No, it's somehow negating everything, right? It's giving you negatives of area. So this is where it causes conceptual difficulties. Right? So let's try to figure out what we would do if we didn't know the y equals 0 case. Okay? But we'll try to mimic that. And we're going to see if this formula works all the time. It's going to turn out it will. Jenna's correct. But let's make sure this is right. Okay, so let's draw, well, let's see. We'll draw suggestively a curve above and one below, since that seems to be the case we're interested in. Okay, but we're going to try to make an argument that doesn't rely on that knowledge. Okay, this is just a guide picture. So this will be A, this will be B, and we want to know what happens when we look at this region. Now, when I look at this region, this here, right, this is your x-axis. this should, if we're talking about areas, this would give me positive stuff, and this would give me negative stuff, right? So I really should have this bit minus that bit somehow. Okay? If you view this as positive, then you have to subtract it to get the actual number. But let's forget all that. Okay? Let's simply apply the same procedure that we did in the first place. Right? What did we do? How did we find the area of some region? What was the method here, right? When we did it over here, we forget about g of x. We just wanted to find the area under f of x. Before we integrated, right, we didn't know what integration was, right? We drew rectangles, right? So we partitioned the interval AB, and we drew rectangles. Right? We drew little rectangles. And we can do the same thing here. Okay? We draw little rectangles. Okay? Now, before we had this problem, right, that the rectangles were missing or adding too much area on the top. Well, now we have the same problem on the bottom, right? We might be not getting all the right stuff on the bottom either. But that's okay. We'll just make our rectangles thinner, right, and add more of them. And again, we're going to be getting better and better approximations. Right? And what are we going to have to what are we going to have to take our limit over, right? We know we're going to have to take a limit as the number of the rectangles we choose goes to infinity. Right? We know that the width of those rectangles is going to go to 0. Right? We know we're going to add up a bunch of them. We know it'll go from I equals 0 to n, right? Everything's going the same. Right? We know that the width of the rectangle is, well, it's this delta xi. Okay, remember that was the width of each of these rectangles. And we know that, well, we're going to have to choose a point in our rectangle, call it, your CI. Right? And then you're going to have to look at, well, maybe where F is at that point. But also, you're going to need to know where G is at that point. And then the height of that rectangle is just going to be whatever this distance is. And what is that distance? Well, it's f of ci minus g of ci. Okay? That's what this distance is. You want to know the distance between things, right? Take the bigger one and subtract the smaller one. Now I say that as if distance is always positive, and of course distance, in some sense is always positive. On the other hand, right, it could be the case that these functions f and g cross. No? So we got to keep that in mind as we go forward. But for now, right, that's the height of our rectangle. Okay, and that's the width of our rectangle. We add up all the areas of the rectangles, right? Then we take the limit as the number of those rectangles goes to infinity, and the widths here are all going to 0. Okay? And this, right, well, this is actually, we already know what this is. This is the integral from a to b of f of x minus g of x dx. Okay, we've already computed that. Okay, so Jenna's suspicion is absolutely correct. All we have to do is subtract. So let's do an example. So let me draw here y equals x squared and y equals x. And I'm interested in this region that they bound. I want to know the area of it. Well, this formula tells me I just need to integrate from the beginning of that region to the end of the region over the top function minus the bottom function. Okay, so I need to integrate from here. What point is right here? Okay, that's 0. And what point is right here? Right, well, how do we know that that's a 1? Exactly, right? The 2 points of intersection are where x squared equals x. And of course, well, if you want, you can solve this, right? X squared minus x equals 0. Factor out an x. And you can see, right? When x equals 0 or when x equals 1, these two functions are equal. So that's how you can tell. So you're always going to have to do this sort of game. When you want to find the area between two curves, the first thing you need to know is, well, what part of the curves are you talking about, right? You have to find the regions, right, that they're bounding. Okay, and there could be more than one, right? Curves could do weird stuff. Okay, so somebody has to tell you, what part do you want? Right? And if they don't, there's just one region, or maybe there's just a couple regions, well, then you need to figure out, right, what interval are you looking at? And you do that by solving, right, the equation where you set one equal to the other. Okay, figuring out for what x's that works. Sometimes this can be non-trivial. I would never, of course, make you do anything that was non-trivial. Okay, so if we want to know this area, I need to integrate from 0 to 1. And now I need to put the top function minus the bottom function. Okay. So what's the top function? It's x, right? So one on top. Okay, now I drew it that way, so you know that. But I mean, normally you would think, shouldn't x squared be greater than x? No, okay, but what's going on here? Why here is x greater than x squared? We're less than 1. When you take numbers that are less than 1 and you square them or cube them, they actually get smaller, right? It's kind of a weird thing. Yeah, they're actually getting smaller. And well, how could you prove that? How could you prove that a number between 0 and 1, and when you square it, okay, so we'll try a half. Yes, a half squared is a fourth. It works. Good. That's 1. Okay, so we just have the rest to go. Pardon? Mm-hmm. Okay, yeah. So if you have a fraction, you certainly, if it's something like this, right? If you square it, you're squaring the top and you're squaring the bottom, and the top you would expect is a smaller number, and the bottom's a bigger number. So this should grow proportionally bigger than the top grows. Okay, so that's kind of a nice argument that you can do like this. Yeah. Okay. What if it wasn't a fraction, though? What if it was just an irrational number? Okay, it's something to think about. Okay, you can prove it, but it's something we should we'll talk about in a moment in my office or something. Some fun time, Okay, but in this case we're right. Okay, x between 0 and 1, x is bigger than x squared, so we just need to integrate x minus x squared dx. And well, this is very easy, yeah. Okay, what's the antiderivative? 1/2 x squared minus 1/3 x cubed. Right? And then, of course, we have to evaluate at 1 and 0. Right? Well, the 0 is really nice. When we plug 0 in for x, everything just dies, right? So we just have to plug 1 in. And that's really nice because 1 squared and 1 cubed are both 1. So you just get a half minus a third, which is 1/6. Cool. So that's the area that they bound, is 1/6. Neat. Now, there was another way we could have determined that based on something we've already done. Yesterday, we computed the area under the curve y equals x squared between 0 and 1. Right? We did this integral from 0 to 1 just at x squared. And do you guys remember what this turned out to be? I was so impressed by this. It was 1/3. And of course, if we draw the line y equals x here, that gave us a triangle. Right? That's how we approximated it. And we said, oh, well, that triangle is height 1, base 1, so the area is 1/2. So, of course, the missing area must be 1/2 minus 1/3, which is 1/6. No? Okay. But nonetheless, there it is. Okay. So the trick, I mean, once you get down to an integral, then you should be comfortable. Because all you have to do is find an antiderivative, which you guys are becoming pros at. Evaluate. This is just brute force computation. No problem. Right? The tricky part of doing this is figuring out, right, what are your limits of integration and which function is on top. Okay? That's the two things you got to do. What are the limits and who's on top? Don't laugh. There's nothing funny about that, Leif. There's no difference between x minus x squared and x squared minus x? How do you mean there's no difference? I mean, of course, if you just swap the order, you'll get a negative out, right? Okay, so I'm not sure exactly what Kaiwei's getting at, but let me try to come up with something you might say. When we're talking over here in the first quadrant, right, or the upper half plane, all right, when we're just talking about area, we don't worry about any negative area that pops up here. Okay, we're just talking about area. Well, what if you computed this backwards? What would your answer be? Right. It would be the same thing, but with a negative at the front, right? Because swapping this order just means multiplying by -1. So it's just going to put a -1 on your answer. So let's say you did it wrong. Okay? Let's say you thought, oh, x squared is certainly, it's always bigger than x. Of course, you square, it gets bigger. Right? And you get out a negative area when you're talking about something which is completely up here. What can you deduce? It's wrong, yeah? You can't get a negative number when everything is greater than 0. Yeah? Okay. Does that same argument work, though, if you have things that are positive and negative? Well, let's see. If I had something which had positive and negatives, then it's possible that the answer could be negative in the end, right? Yeah. I mean, let's say I had something that not only got this area up here, but also did a lot of this area down here. Okay, so these things would cancel out, right? And maybe this one is even a little bigger, and so it gives you a negative number out. Right? Okay, that's the right answer, a negative number. Right? But if you always took the rule, oh, I can't get a negative number out, then you'd be doing it wrong. Right? If you tried to swap it. Okay. So the only way that you can, if you know everything is positive, then it doesn't matter. You can just put it in any order you like, and if you do it wrong, just let me put a minus sign everywhere. Boom, I'm happy. I'm right now. Okay. But only when everything is positive. Okay, now I'll give you some problems to work on to get some practice with this stuff. But I want to spend what will probably be the balance of our time today talking about an application of this in economics. And it's something called the Lorentz Curve. And it's related to something else called, well, I may not get the pronunciation right, but I'll call it the Gini Coefficient. I'll spell it for you, and then somebody can tell me what they think the pronunciation should be. So this curve has to do with income inequality. And before I begin, just for anybody here or watching at home who tends to get offended, I am not trying to make any argument for or against any policy geared at either accentuating or eliminating income inequality. I'm merely making an exposition on a tool used by economics to measure income inequality. Is that a reasonable disclaimer? Okay. So, all right. So, what does income inequality has to do with? Okay. Well, you probably heard expressions like 75% of the wealth is controlled by 25% of the population, right? Or 90% of the wealth is controlled by 40% of the population, something like this, yeah? Right? So, and everybody's, oh, how horrible, you got to get those bastards, that sort of thing. Okay, so here's a question, right? As an economist, how would you go about measuring income inequality, right? What are you really driving at? So what we're going to do is we're going to set up a nice little graph. Okay. And on the x-axis, we're going to put households, or sometimes you might think percentage of households, but I'm just going to actually set this up to be between 0 and 1. So any percentage, you just divide by 100 and you get a decimal between 0 and 1. All right. And then up here, I'm going to put income. Okay, so, and again, this is also going to be between 0 and 1. Right? So 0 represents 0% of the households, right? And 1 represents 100% of the household. 0 represents none of the income, and 1 represents 100% of the income. Right? So what you might suspect is that as you increase the number of households that you're looking at, right, then the amount of income that those households make is going to go up as a percentage of the total income. Right? So if you look at all of the income, right, then that should be, you should only be able to get all the income by looking at 100% of the households. Right? Or at least it should be the case that if you look at 100% of the households, you should get 100% of the income. Okay? On the other hand, if you look at none of the households, there should be no income. Yeah? Okay? And you might have something where you say, okay, let's look at just 20%. Right? So this would be 0.2. So we'll look at 20% of the households. And if we look at 20% of the households, then they might be, I don't know, let's put them up here. The top 20% might have, I'll say 60% of the income. So you can have things like this. Of course, now I have a scaling problem. Yeah. So first thing I'm going to do is draw a little line here just to help me with that problem with my scaling. All right. So this first line is what is sometimes called the line of perfect equality. Right? This is where everybody has the same amount. Okay, so if you have 20% of the households, you should have 20%. Yeah, I guess I'm doing this backwards when I try to put it up here. It should actually be the other way. If you have 20% of the households, they should have 20% of the income. Right? If you have 50% of the households, right, you should have 50% of the income, right? That's if everybody has the same income. Okay, that's the line of perfect equality. Right? Now, what would be perfect inequality? As bad as you can imagine. Yeah, well, yeah. What if you just had 0, 0, 0, 0, 0, and then when you finally got to Bill Gates, all right, he had all the money. Okay, this would be, this is the most unequal as you can imagine, right? That would be bad. Okay, now I think that I can say without proof that we are not in either of those two situations. Right? It is certainly not the case that there's only one person with income. And it is also certainly not the case that everybody makes the same amount of money. Yeah? Yeah. So if you take all 100% of the households, right? If you take 99.999% of households, they have no money. But then when you go to 100% of the households, if you look at all of them in the aggregate, then you get all 100%. What would be a vertical line if we it wouldn't. It wouldn't mean any. I mean, it would mean that nobody had all the money. But not. I mean, yeah. That is, there is nobody, and yet they have all the money. So it would be meaningless. You can never, you can never go above this diagonal line here. That's what it should mean. Okay. Yeah. So the heavy hitters should be on this side. That's the point, and the poor people should be down here. Okay. So now, of course, in reality, when you sit down and try to draw, right, what the actual data points are, this is kind of a discrete thing. Okay. But we kind of smooth it out, and we make a little continuous curve. Okay. And it might look something like this. Okay. And this curve is called the Lorentz curve. Okay, so this is supposed to tell you, right, if you want to know how much of the income is controlled by, a certain number of the percentage of the households, you just go to that point on the curve and then say, okay, that's how much of the income, right, they have. Okay, so I'm not trying to draw this realistically based on any given country, just some version of the curve. Now, how do you actually measure the income inequality? Right? And the way it's done is by computing the area between the line of perfect equality and the Lorentz curve. Right? Notice the similarity here between the two examples, right? This y equals x, that's your line of perfect equality, and then, well, this would be your Lorentz curve. Okay, so now it's clear why it's a good idea to know how to do this problem, right? You want to figure this out. And then the way you actually, the number that you take, you don't just take this area in here. You actually compute the ratio. So the ratio of this area to the entire area of this triangle. Okay, of course, since I've done everything scaled to 1, what's the area of this triangle? It's 1/2. So you take this number, right, this area, you divide it by 1/2. Of course, dividing by 1/2 is the same thing as multiplying by 2. So you basically take this area and multiply it by 2. Right? So whatever this area is, this area multiplied by 2 is called the Gini or Gini. I would say Gini, but I'm sure. I've only read about these things. It's called the Gini Coefficient. And well, it's been a while since I was looking at these things, but from what I recall, this is maybe the most popular of the ways of measuring income inequality. Right? So if you go online, you can probably find for any country in the world the Gini coefficient. And the Gini coefficient, of course, right, is going to be a number between what? Well, the smallest this area would be 0, right? That's if you had perfect equality, right? If this Lorenz curve was actually the perfect line of perfect equality, then you'd have 0 times 2, which is 0. Right? On the other hand, you could also have it where you had the Bill Gates scenario, right? In which case you'd have the full 1/2 times 2, which would be 1. Right? So if I call the Gini coefficient G, right, then we know that G is somewhere between 0 and 1. But when you read statistics, they usually multiply by 100 to take you back into the kind of the percentage situation. Right? For instance, I think last I looked was probably a couple of years ago. I think the U.S. Gini coefficient was about 46. Right? In Europe, they're typically more around 30. Right? In the poor countries, I've seen them up as high as 75. So it goes around. Now, there's some caveats here to the usefulness of this. One, this just gives you a number. That's all it does. It gives you a number out. And if I change the shape of this curve, I could keep the same area, right? but change the shape of the curve, right? So shift things around a little bit so I get the same Gini coefficient out, but the income distribution is different, right? So this doesn't take into account the shape of the curve. Okay, so that's important. Of course, if you're doing public policy, it's important to know, are there some really, steep sectors at certain points, right? It's a big difference to be having this nice kind of, rather gradual, smooth curve and something that looked like this. Right? Now, of course, you can tell automatically this has much bigger area. Okay? But I could adjust, one of these to have more comparable area. Right? For instance, I could shoot up here. It should be very close to inequality or equality here, right? And then go. And if it looked like that, okay, now what's going on around here, right? This definitely has to change the way public policy works, right, as opposed to this one. Right? On the way over here, so I know you guys hate when I write things down on the way over. I just wrote down a few things that it's important to think about when you look at these sort of measures. So first, and this is not mathematical. This is just thinking about these things. First, income. What should count as income? Well, should it just be the money that you make at work? Should we include money that you earn from selling stocks, capital gains, right? Real estate investment? If you stay at your parents' house and they give you free rent, should that count as income? Right? These are all questions you have to answer when you start deciding these things. Right? On the other side, households. Should we look at entire households or should we look at individuals? Right? If people pool their resources as a household, that makes a big difference. Right? Here's another thing. When you look at these statistics online, they're always for a given year. Right? Does it matter if you look at just the current year over somebody's lifetime, how much income they make? Should that make a big, that somehow could make a big difference, right? While we're at it, look at somebody's life cycle. My kids are a drain on my economy. They bring home no income. They just suck and suck and suck all my resources away, right? Nothing. They do nothing, right? Okay, fine, but they'll get older, and eventually they'll start to make money, right? Okay, so then they work and they work, and their income goes up, their income goes up. And then they get into their 50s and 60s, and what starts to happen when you get into your 50s and 60s? People start to retire. And what happens to people's income when they start to retire? They go down. In fact, they might even go negative. Right? Now, this whole setup actually assumes you always have positive net income. Okay? But yeah, people start to just consume, and they don't have any income. Right? How should that affect how you talk about income inequality? Right? Do you really want to talk about somebody who's 75 who can't work anymore, who makes no income at all? Is their life story relevant to the discussion of income inequality? Right? These are questions you have to answer. What was another one? Oh, inflation. Yeah, this is another one. Inflation isn't really built into this. Right? And let me give you an example with capital gains, right, which is under the income heading. Let's say I buy a house in 1960, and it cost $70,000 in 1960. Pretty expensive house back then. And let's say I sell it today for $150,000. How much did I say I bought it for? 70. So I made $80,000, right? So I should be liable for capital gains of $80,000. On the other hand, the economy, doubled, tripled, quadrupled, whatever, right? Inflation made it so that $150,000 maybe is only worth $65,000 today. So did I make $80,000 or did I lose $5,000? Right? Well, as far as the tax law is concerned, you made $80,000. Just you have to know that, right? Whenever you're buying and selling anything and you make a capital gains, they don't care about inflation, right? But if we're thinking about this and we want to make a reasonable measure of income inequality, that's something we at least have to consider. Do we want to include things like inflation when we talk about income? This was the last one I put on right before I came in here. Let's say that you're really poor, like I've been for a long time. You learn how to stretch your dollar, right? You learn, what foods you can really afford to buy and how you can make them stretch, right? You learn what necessities really aren't necessities, yeah? Okay, so maybe you're more efficient if you have lower income inequality, if you have lower income, which actually somehow raises your standard of, raises your income. On the other hand, you might think, well, no, rich people actually are more efficient at spending their income, right? For instance, they get much better savings rate at banks. Right? It's much easier for them to do that sort of thing, right? They can buy things in bulk much more easily, right? Right? They can do all sorts of things where they have good contacts with people and they know how to get into the wholesale club and they can. There's an argument for both sides, right? That it's not just your income, but how efficiently you spend your income, right? That's already a question. Do the effects of income inequality come from the income inequality itself, or the way income is spent, right? How efficient it is. And the last thing that I want to point out is, in the end, this is just a number. It points out income inequality, right? And it's some measure of it. But it is not prescriptive. Okay? It's not telling you what to do. Right? That's what public policy makers have to do, right? They have to figure it out. Not only that, it doesn't tell you the causes of those inequalities. This is just a way of comparing situations. And it's up to people to actually to say, okay, look, if you just maybe look at one country, it makes sense to compare, right? Or maybe similar countries. Does it make sense to compare the U.S. Gini coefficient with that of Zimbabwe? Right? You have to make an argument why or why not. Okay, so just always you have to think about these things. Mathematics is a very nice tool, and it's a very nice way of taking some real-world information and processing it into a number that tries to tell you things. But be wary when people try to draw conclusions from those numbers, when they don't tell you exactly what those numbers mean. Okay, so just a little side piece for you guys. Yeah, we got 5 minutes left. Let me just introduce what we're going to do next time. I decided to push off the discussion of volumes a little bit. I first want to talk about arc length. And so today what I'll just do is I'll set this up, and then tomorrow we'll do some more examples, finding these areas, and then computing these arc lengths. Okay, so here's the situation. Right? I have some function, and it kind of snakes around like this. And instead of asking what the area under the curve between A and B is, I actually want to know the length of this line. Right? Now, if we were talking about a square, this would be easy, right? We would just say, what's the perimeter of the square? And you'd say, well, each side has the same length, so multiply one side by 4. Voila. Yeah? And if it was a circle, well, we'd think, okay, yeah, a circle has a circumference. The circumference is 2 times pi times the radius. Right? Okay, no problem. But what do we do with some weird squiggly lines? Rectangles again. Well, of course, if I do rectangles, then I'm getting all this area that I don't really care about, right? But you're not on the wrong track. Right? So when we wanted to find area, we approximated, right, this area with rectangles, something that we knew how to find the area of. Okay? If I wanted to approximate this curve with something that I knew how to find, well, instead of area, distance, what's the most basic unit that we know how to find the distance of? A straight line. Right? That's somehow the most basic. So here's a first approximation. Just connect the dots. Right? La, 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 la. You guys are probably too young to know Pee-wee's Playhouse. Gosh, I feel old. No? Okay. So, of course, yeah, this might not be too bad of an approximation, right? This thing, has a lot of length above and then goes below, and maybe if you took this and straightened it out, a little bit, it'd be close to this line. But there's no way we're actually getting the right length here. Right? So if one line doesn't cut it, what might be a better way to approximate it? Still using straight lines. Did I just erase the actual curve somehow? How did that happen? Okay. Well, what if I pick some points in the middle? Okay, I'll pick a point there, and I'll pick a point there. I'll pick a point there. Okay. And now I connect the dots. Question, is it more likely that this is the right area than before? Well, probably not. I mean, the chances of them actually being the right area is 0 in both cases. But yeah, you can see this is certainly getting closer. Right? Now, if you were drawing a map of the world, could you actually draw the real coastline on your map? No, of course, you can't do this, right? So what do you have to do? Well, you have to just kind of draw little straight lines that approximate it. Yeah? Right? In fact, it's not so easy, actually, for anybody to even draw a curve. You think about it, if you tell a printer to draw a circle, do you think it's really drawing? Yeah, well, actually, it probably just does points, right? Doesn't even connect them, right? They're just so close together that we can't tell the difference. Yeah? So, but it's certainly the case, right, that, okay, I could start adding in more of these dots. Right? Now, how many dots do I need to get the right answer? How many rectangles did I need to get the right angle? Area, right? Well, yeah, you needed to somehow go through this limiting process again. So tomorrow, what we'll do is we'll start adding more points to this, right? And say, okay, yeah, you start approximating this with these little lines, and eventually you're going to be getting the right area in the limit. And this we'll get a formula out for it. It'll be very nice. It'll be cute. And then we'll do some examples. And that will be all of, and we'll do some more examples of this area between curves and so forth. And that will be all the material that we cover for the midterm.